Dear students, today we will discuss about the Gauss theorem, which is again related to irrotational motion. I am writing the statement of the theorem and then I'll explain it. The theorem says that naturally the fluid is ideal and homogeneous if a region V is fully immersed in the fluid. That means the volume which is considered is fully immersed in the fluid, and is bounded by a spherical surface. Bounded by a spherical surface, then such that the flow is irrotational throughout V. This may be written in another way. Flow is irrotational throughout V. You can also write in place of this such that delta 2 phi is 0 everywhere inside V, where what is phi? Where phi is velocity potential function. So in another way it is the irrotational flow, velocity potential function. Okay, then the mean value of phi is equal to its value at the center of the sphere. So this is the theorem. This is about mean value of velocity potential. So what we do, we have to find phi m, and as per definition, what is phi m? Phi m is the mean value, and you have taken the spherical surface, so mean value will be phi ds. Suppose phi is the value somewhere at somewhere on the surface. Phi is velocity potential at an arbitrary point for the surface S. So if it is phi for one point, for ds it will be phi dot ds, and because you have to take the mean value, so you will divide it by surface area, that is 1 upon 4 pi r square. So I have to talk about this. What is the value of phi m? Rather, I have to talk about what is the variation in phi m. Okay, so we will handle it later. First of all, what we do, we take a sphere. It is a sphere of unit radius. It is a sphere, and you take, I am taking the bigger one outside. I am taking this sphere such that it is containing the point P as origin. Now you cut a conical cross section from it. Because it is a sphere, on the base you will get something like this. Similarly, it will cut this another section in the concentric sphere. Okay. So I have taken a cone at P. Outer sphere is having the radius r, and inner sphere is having the radius unit. Suppose this is theta. Then you have consider a sphere of radius r with center at P and a concentric sphere of unit radius, the same center P. We have seen the concentric, it means the same unit sphere with center at P. Concentric sphere of unit radius with the center at P. Now cut a conical section. When you cut a conical section, on the surface it will describe an intercept and it will describe an intercept such that it describes intercepts say ds and dw at the outer and the inner spheres respectively. Now you will have certain relations, like what will be ds, this is ds intercept. Definition, ds will be r square d theta, and what will be dw? dw will be unit square d theta. D theta is the angle made by the small intercept, so I may also take it d theta. Okay, and from the two you get ds is equal to r square dw. I may need this relation. Now second thing is that it is said that phi is the velocity potential. So another condition is that given that delta square phi is 0 inside the sphere. So it is 0 everywhere inside the sphere. It is also a condition. Now we again come to our phi m. Phi m was 1 upon 4 pi r square phi ds for the surface S. If I replace this ds by dw, then it will be phi r square dw from that previous relation, and now this will be around s dash, not around s. Now your s dash is of unit radius and it is independent of r, so I take this outside, r square upon 4 pi r square s dash phi dw. R square is cancelled with this, 1 upon 4 pi phi dw. Now find delta phi m delta r. What is the variation of phi m with respect to r? This is s dash, 1 upon 4 pi delta delta r s dash phi dw. This s dash is of unit radius, it is independent of r, so you can interchange the integral and differentiation. 1 upon 4 pi s dash delta phi delta r dw. Again write it as delta phi m delta r is equal to 1 upon 4 pi s dash. Now I will again change this s dash. First I'll write 1 upon r square delta phi delta r and r square dw. What I did? I multiplied it and divided by r square. And it will be, because s dash is free from r, 1 upon 4 pi r square delta phi delta r square d omega. This can again be replaced by ds, but I will replace it in the next step. 1 upon 4 pi r square s delta phi delta r, because I am writing ds in place of it. 4 pi r square. What is this delta phi delta r ds? It is in actual delta phi dot ds, which may again be written as 4 pi square integral delta of delta phi dv by Gauss divergence theorem. I'll put dot here because now it is a vector and it is a vector. 4 pi r square delta 2 phi dv. But what is delta 2 phi? This is 0. So it is 0. So phi m, when you are saying that this delta phi delta m, delta delta r of phi m is 0, it implies phi m is independent of r radius. So when r shrinks to 0, tends to 0, that means your point is approaching to center. This implies as we approach to center, phi m remains same. So this implies phi m is equal to phi, it is the value at center. Value at center. So this was whatever is said in the theorem, that the mean value of potential will be the same as its value at the center. So it is all about its proof, and it follows certain corollaries. Like one corollary is that, which is very simple and very interesting, that phi cannot be a maximum or minimum in the interior of any spherical region. Okay. So in this corollary we will suppose that phi maximum or phi minimum exists somewhere inside the spherical region. Okay. Let phi maximum, whatever I will do for phi maximum, you may easily do for phi minimum. Let phi maximum exists at a point interior to the surface, interior to the sphere, and this is sphere of radius r. Let r be very small, r is tending to 0. Then this implies phi maximum is the value of phi at center. But we know that phi mean is the value of phi at center. So this implies, because it is the maximum, that phi maximum should be greater than phi mean. But you are saying that these two should be same, because it is also the value at the center, this is also the value at the center. So you get a contradiction, which is not true, so it is a contradiction. And this implies that phi cannot be maximum in the interior of any spherical region. Phi cannot be maximum in the interior of any spherical region. The same way you can prove it for phi minimum. You take phi minimum to be existing at some point in the interior of the sphere. You approach that phi minimum to the value at the center. Then you will write phi mean is greater than phi max, phi minimum. In that case, you will get a relation phi minimum is less than phi mean, while these two should be same by the theorem. So again you will get a contradiction, and you can say that phi cannot be minimum in the interior of any spherical region. So this is a corollary of Gauss theorem, and this is all about this chapter of irrotational motion. So thank you all.